So in this video we're taking a final look at Unit 2 and we're focusing on the last part of consumer products and energy from fuels, and that is how to measure the energy that is released when fuels are burned. Now, as we've discussed, there are many types of fuels. So the fuels we obtain from crude oil, for example, are called alkanes specifically, and they include methane, the gas that's used in homes, and propane and butane. For example, they're used in camping gas cylinders, and octane, which is a component of petrol that we put in our vehicles. But there's also the alcohols, which are another source of useful fuels, and they're made often by fermentation of carbohydrates made by plants. And alcohols actually burn more efficiently than alkanes, as they already have some oxygen in their molecules to aid that complete combustion. And there's two alcohols specifically that are used as fuels quite often, and they are methanol and ethanol. But that aside, we want to focus on, regardless of the fuel that we're using, how do we quantify the energy that is actually released when they are burned? Because of course, as we've just said, some will release energy better than others, more efficiently. Some will release more energy, some will release less. So we want to be able to know exactly how much energy is being released. And we have an experiment and a formula that can help us work that out. So by burning fuels and collecting the heat energy, the quantity of energy released by burning a fuel can be worked out using this formula here. So we take E with a little h, and that equals C M delta T. And that little triangle means delta. And we're going to look in detail at what each of these units, each of these quantities actually means, and how we can use them to figure out energy released. So first of all, we'll just start and we'll go left to right. We have E with little h. Now E, whenever you see capital E, you should immediately be thinking that this is some kind of energy quantity. And in this case, it's the heat energy produced. And you can remember that using the little h. So we're talking about enthalpy. So heat energy produced, and we always want to make sure we're giving that value in kilojoules if we're asked. So how do we figure this out? Well, we take C, make sure you use a little c so it doesn't get confused with carbon, and this is called the specific heat capacity. Now this is a value that is constant, it doesn't change if we're talking about water, right? Because each compound will have a specific heat capacity. But in the examples we're going to look at, 90% of the time we're going to be talking about raising the temperature of water by burning a fuel. So the specific heat capacity that you'll have to know is this 4.18 kilojoules per kilogram per Celsius. Now, you don't have to worry about remembering that because it's in the data book next to all of your formula that's listed on page 3. But just remember that it's specific to the substance that you're talking about, and 4.18 is specific to water. Next up we have the M, and it's a little m, which means we're talking about mass. And in this case, it's the mass of water heated. So there's that water coming into it again. We're going to look at a diagram in a second of why we're talking about water specifically. But we're talking about the mass of the water that is being heated up by burning our fuel. Now, please remember, it is not the mass of the fuel that is being burned. Okay, that's actually not used in this calculation. It's the mass of the thing that's being heated up. In other words, it's where the energy is actually going. That's the mass of the stuff that we're actually interested in. And we always want to give that in kilograms, which might be tricky to remember, right? It's not grams, as it's often quoted in questions, it's kilograms, because we have to tie it in to match with our specific heat capacity. And then last up is probably the more complicated one, that is the wee triangle and the capital T, so delta T. Now, whenever you see delta in chemistry or science, that means a change in something. So the amount that something has changed by. So delta T means change in the water temperature, and that is given in degrees Celsius. So that is how we notate our quantities. Now we want to have a look at what that might actually look like in the lab. So if we go to an example, a setup that might use those values would look something like this. So we'll have some kind of vessel, usually a metal can, in this case a copper can, and that is because metals like copper are excellent conductors of heat. So when I'm burning my fuel in this case it's a little methanol glass burner. When I'm burning my fuel, I'm making sure that most of my energy that comes off of the fuel is going into whatever is in that can. If we use something else, it might break or it might not transfer as much heat energy. Not included in this diagram would be some kind of guard, so some kind of paneling at the sides, and that would often be there to ensure that no heat energy is lost, to wind or the candle being blown or anything like that. But in this case, it's just a plain setup. So we have our copper can filled with water, specifically 100 centimeters cubed of water, and a thermometer in there to detect the temperature change of that water. So as I said before, the focus in this experiment setup here is really all on the water. We're not interested in the temperature change or the mass of the fuel. It's the temperature change and the mass of the thing that we are burning, which when you think about it makes sense. So let's have a look and see how this might come up as a question at National 5. So let's have a read. It says, the following apparatus was used to calculate the energy released when some methanol was burned. The following results were recorded. Start temperature in degrees Celsius is 19, then the experiment proceeds. And then the final temperature in degrees Celsius is 54. So our task then is to calculate the energy released in kilojoules. So a couple of things to point out here. One, we're going to have to use information from the diagram because there are values given. And two, we know it's a calculation specifically because there's that magic word. It will always say calculate X. In this case, X being the energy released. So let's have a look at how we would lay that out and how we would figure out an answer. So I would always start by writing down the formula as it's quoted in the data book. So that is EH equals Cm delta T. Always write it in that form to get started. Our next task is then to write down each value and what we know about that value. So if we know it or if we don't. So EH is the energy released. That is what we're trying to figure out specifically in this question. So we don't know that. So we're going to put a question mark there and a circle because that's going to be our focus in trying to figure that out. Now for the C, now as we mentioned, we're dealing with water, and C is the specific heat capacity, which we now know for water to be 4.18. And we can leave it at that because we know that it's about water. The M is the mass, and this is where we have to be careful because in the question, if we look back at our setup, we are told that it's 100 centimeters cubed of water. Now, do not be tempted to write in 100 for the mass, because remember, the mass has to be quoted in kilograms. So what we have to remember is that 1 litre of water is equal to 1 kilogram of water. Okay? So we have to have 100 centimeters cubed, and we're going to divide that number by 1,000 to convert into kilograms. So that's going to give us 0.1 kilograms. So if you're given in centimeters cubed, divide by 1,000 to get into kilograms. And then last but not least, our temperature change is not an individual temperature that's quoted, it's the difference between them, it's the change that happens. So we've gone from 19 to 54, so we have to figure out the difference between 19 and 54, so we will take 19 away from 54, and that will give us 35 degrees C. So now we have all our values, 4.18, 0.1, 35, and we just need to substitute them into the equation and then we'll be done. Okay, so we're going to write out our equation again just to keep us right. EH equals C M delta T, and remember, if we have no operators between values in an equation, that just means multiply. So E is going to be equal to 4.18 times 0.1 times 35, and then all I'm going to do is put all of that in my scientific calculator at the same time. So we're going to have 4.18 multiplied by 0.1 multiplied by 35, and that will give me 14.63. So I write down 14.63 0.63, and I'm going to give that answer in kilojoules, remembering to include my units. Even though they're given in the question, it's good form to include my units. So that's great. We now know how to work out the energy released in kilojoules if we know the specific heat capacity, the mass of water that we've raised the temperature of, and the temperature change of that water. However, questions will often ask it in a roundabout way. They might give you the energy released quantity, the change in temperature or the mass, and you have to figure out one of the others. So it won't always be the energy that you're figuring out. Sometimes it will be the temperature change, sometimes it will be the mass. So in those cases, you're going to have to rearrange the equation to suit what it is you want to figure out. So we'll have a look at an example of that just now. So example 2 says ethanol can be used in portable camping stoves. Okay, the chemical reaction in a camping stove releases 23 kilojoules of energy. If 100 grams of water is heated using this stove, calculate the rise in temperature of the water in degrees Celsius. So already this is quite different because we're given the energy released and we're given the mass of water. What we have to figure out, because it says calculate, is the rise in temperature. So in other words, that's the temperature change, and we have to do that in degrees C. So once again, as I said before, always write out our equation in the same way, and then write out the values that we have and the values that we don't have. So in this case, we do have the energy released. It's 23 kilojoules, so we'll write in 23. We do have the specific heat capacity, even though it's not quoted in the question, because we're talking about water. And remember, water specific heat capacity is 4.18. The mass is 100 grams of water, but remember we want it in kilograms. So to get from grams to kilograms, we have to divide by 1,000, because we're dealing with a smaller number here. Bigger quantity, smaller number. So it's going to be 100 divided by 1,000, which equals, again, 0.1. And then this time, the change in temperature is what we're trying to figure out. So question mark in a circle or an X or whatever it is you're happy with as an unknown. So now what we're going to do is we're going to take our equation and we're going to say, okay, this isn't directly useful because I don't want to figure out this. I want to figure out this delta T. And right now, it's got an M and a C in the way. We want to get them out of the way. So there's a couple of ways you can think about doing this. You can think, well, whatever I do to the left-hand side, I have to do to the right-hand side. Or you can think, change the side, change the sign. One of those concepts might be familiar to you from maths. I'm going to do change the side, change the sign. So basically what I mean is, any operator on the right-hand side that I want to move over to the left, whatever it was doing on the right-hand side, I need to do the opposite with it on the left. So for example, EH stays where it is, and I want delta T on its own. Right now, C and M are multiplying delta T, so if I take them over to the left-hand side of the equation, they are now going to be dividing EH, because they were multiplying on the other side. So I can do them individually. I can take the C over, and I can take the M over. And now, I can say that delta T equals EH divided by CM. Now, if you don't understand what I did there, another way you can think about it is, okay, if I divide EH by CM, I also have to divide the right-hand side by CM. If I divide CM delta T by CM, the C's and the M's cancel and they disappear, leaving me with just delta T. So that's the two mathematical methods that you can think of rearranging this equation, but whatever way is most comfortable for you, stick with it and do that for every question. Don't change how you do it. Okay? So if we use our newly formed equation, we can substitute all in our values just as before and get a nice answer. So this implies that's what that little arrow means, 23, which is our energy change, divided by 4.18 times our mass, which is 0.1, and I'll put that in brackets so I know to do it first, equals delta T. So again, I'm just going to put all of that into my scientific calculator at the same time. So I have a fraction button, which is going to help me do this in oneer. So I'm going to press that button there, 23 in the top, move down, and then I'm going to set up my brackets to make sure that the calculator does it in the correct order. So brackets, 4.18 times 0.1, close bracket, and move my cursor out to the right. So that is exactly how to set up the calculator. And then that gives me the answer as a fraction. Convert to a decimal, pressing this SD button here. 55.02, blah, blah, blah. I'm just going to use 2 decimal places. That's a good standard to aim for. I'm going to round down to 2 because it's a 3 after it. So, final answer, 55.02 equals delta T. And remember, we're dealing with a temperature change, so we're giving our answer in degrees Celsius.